All right, so let's take real quick. Let me get your attention here. Let's take an example. I want to take a function and we're just going to analyze. We'll get a little practice with our first derivative test, first of all. Let's do this function. Let's do f of x equals x cubed minus x squared minus 6x. Okay, so flip and close. Let's get everybody taking a look at this. This is pretty good stuff to consider here. We're going to add something much more powerful to our arsenal of weapons that we can apply to functions, to sketch functions, to understand what they look like. What do I want to? If I want to sketch this function using tables, what do I need to do? Well, what's probably, and let's try to articulate some steps now. We've kind of looked at some examples, but let's see if we can get somewhat procedural about this. And just we want to come up with kind of a pattern we're going to follow whenever we're trying to sketch a function, because that's our next big goal, is to be able to take all different kinds of functions and come up with sketches based on symmetry and increasing, decreasing, first derivative test, all that stuff that we know. All the stuff we bring in from pre-calculus too. So what's maybe the first thing we want to do? Yeah, we're definitely going to want to find a derivative, right? What's the purpose of finding the derivative? To find the critical numbers, okay? But before we even start that, it might be useful to know which types of, to know the domain, to know which, where can we actually find critical numbers, right? So the first step is probably always, let's find the domain of our function, if it's not imposed. And it's not. There are no restrictions on this domain. So what is the domain? Yeah, it's all reals, isn't it? Right? It's a polynomial. No red flags here. There's no x's in the denominator. There's no even roots, so we're fine. So the domain of this thing is all reals. Okay. And we could even start maybe building a table if we wanted to. So if we're going to build a table, what are the rows in the table going to be? First row is what? Well, first row is x, right? So we want to know, and think of that top bar as just being the x-axis. And we already know what the domain is. The domain's going to go from negative infinity to infinity. What's the next row? F of x. And that's there so we can get ordered pairs, right? Values of the function. What's the next row?
F prime.
F prime. Okay, that's all we got, right? So let's take a derivative then. What's F prime? Okay, good. And how are we going to use that? Okay, we're going to want to factor that, aren't we? And how come? Where do we find critical numbers? Where the equal to 0 or undefined. Is our first derivative undefined anywhere? No, it's nowhere undefined, but we could set it equal to 0 and find maybe some other critical numbers, possibly, right? So I'm going to indent a little bit, and I'm going to say f prime equals 0 when 3x squared minus 2x minus 6 equals 0. Okay? All right, so how are we we got a quadratic equation that we need to solve. How are we going to solve that?
Factor it.
Okay, if we can factor it, we'll factor it. So to find out if it's, talk to me about quadratic functions. This might be some stuff you've never thought about before. We got multiple methods of solving a quadratic equation, right? Really, we want to be as efficient as possible. How do we know which method we should use? I mean, sometimes it's obvious. If there's a single x in our quadratic equation, what would we do? Like, I'll give you a quick example. Like, what if we had something like this? What if we had what if our quadratic equation was written in a form where there was a single x? So what if I had something like 2 times the quantity, 3x minus 1 squared plus 7 equals 92? What would you do? Well, I mean, you could, right? We could expand this whole thing out and put it in standard form. But why? I mean, this is like set up for, it's a pretty easy problem now.
Yeah.
What can I do here? What can I do? I mean, I thought I heard an answer.
You just try and isolate the parentheses, so you subtract 7 and then divide by 2.
Okay, good.
And take the square
Good.
root.
Yeah, and there's a real simple strategy there. If I'm solving a quadratic equation and I can point to a single x, then my strategy is always isolate x, right? You get my point? So what would, and I'm not gonna do the whole problem, but you guys could all do this. What would the steps be to isolate x? First I would subtract 7, then I would divide by 2, then I would square root both sides, and then once I've square rooted both sides, I'm gonna get a plus or minus on the other side, right? I'm gonna add 1 in front of the plus or minus and divide the whole thing by 3, right? And simplify. You guys, but that's easy, right? That's a relatively simple thing to do. So in that case, it would be very straightforward and simple. What if I can't point to a single x? Then I've got some other options, don't I? If I'm not isolating x, think back to Honors Algebra 2. What were the methods you had? You could factor, you could complete the square, or you could use quadratic formula, right? Okay. And you might just always default to the quadratic formula, but I would argue that really you probably shouldn't. The quadratic formula is a little bit messy because you've got to simplify a radical, and there's some computational stuff there, right? So how do you know which one you should do? There's a really simple way to tell. Remember talking about the discriminant? Okay, but instead of just remembering the discriminant, think about the quadratic formula for a second. We can identify A, B, and C here, right? We always want A to be positive when we put this in standard form. So if that were negative, we would just multiply both sides by -1 to make it positive, right? To make A positive. It's give you the same solutions. In the quadratic formula, x equals what? What's the quadratic formula?
Negative b plus or minus the square root of 4ac.
No.
B squared.
There you go. B squared
B squared
minus 4ac, all divided by 2a. Well, the discriminant is the part that discriminates between the types of solutions you could possibly get. You could either get 2 real, or 2 imaginary, or 1 double root, right? Why is that? Well, this is the part that's under the radical, right? So in what case would you get complex solutions with imaginary parts? If that's negative, right? So that's the discriminant, the b squared minus 4ac. If that's negative, you know that you're getting complex zeros, right? If it's positive, you know you're getting 2 real zeros. If it's 0, then you're getting negative b plus or minus 0. Well, it's the same thing, right? So you're getting 1 real solution that counts as a double root, okay? There's a little bit more that it tells you too. In what case would we get solutions that are rational versus irrational? Think about this one. What's it mean to be a rational number? Number that can be written as what? Well, I mean, it could, but it doesn't have to be a whole number. Okay, yeah, so as a decimal, it would be a rational number would be one that terminates or repeats as a decimal. But I don't need any of that stuff. What does it mean to be a rational number? What's the word ratio mean? Well, I mean, really just, if you're comparing, it's just a fraction, isn't it? Ratio means fraction, so at its root. A rational number is just a number that can be written as a fraction, right? Everybody buy that? Okay. So a fraction that doesn't have, irrational would be one that can't be written as a fraction. Okay. So how does the discriminant play a role in determining whether your answer, whether it's complex with imaginary parts or real, can be written involving fractions if it's rational? And I guess rational number wouldn't be complex, would it? Wouldn't have any imaginary parts. So let's say if we know it's real, how does the discriminant play a part in determining if our answer is going to be rational or irrational? In what case am I going to, give me examples of irrational numbers. Say it again. Okay, square root of -1, in fact, that's imaginary, isn't it? How about real numbers that are irrational? Square root of 2. Square root of 3. Not square root of 4, because the square root of 4 is 2, right? That's rational. But the square root of any number that's not what is going to be irrational? It's not a perfect square, exactly, right? So look, we could, if we were to quickly, and this is something you can do mentally, if we're going to calculate the discriminant, that's not hard to do, b squared minus 4ac. If I get an answer when I calculate the discriminant that is a positive perfect square, what's that tell you? If it's a perfect square, when I square root it, I'm getting a rational result, right? And then I'm going to end up getting a rational number because I'm going to get some number plus another rational number divided by another. I'm getting a rational number regardless, aren't I? Okay. Good. And if I know it's rational, then I know that factoring would work. Okay? I know that factoring would work and that completing the square wouldn't be horrible either, right? But factoring would work. Okay? So if the numbers are not ridiculously big numbers, we could, you guys probably learned bottoms up for factoring,
Yeah.
right? Have we talked about bottoms up in here?
It's been a long time.
It's been a long time?
It's like
Okay, this is probably some necessary review, I think. This is one of the best things about calculus, one of the very best things as a math student, is that you get an opportunity to kind of bring some things up and maybe add a little bit, fill in some gaps that you have, and that's almost more important than the calculus, I think, moving on to college. So let's try this example. If we calculate the discriminant for this function, what am I going to get? b squared minus 4ac. I'm getting 4 minus negative 72.
Yeah.
So that's 4 plus 72 is 76. Is 76 a perfect square? No, it's not. So I wouldn't probably, I'm not going to try to factor it because I'm not going to get an easy factor then. My factor is going to involve square roots and nobody wants to do that, right? So this is one where we would definitely just throw it into the quadratic formula. In what cases might we want to use completing the square? And it's pretty limited, really, I think.
Isn't it just when you have an x squared plus a number?
Okay, if we had an x squared plus a number, and I'll go one step beyond that. If the number here is even, it makes it a lot easier, right? Because think when you complete the square, you've got to take half of b and square it. Well, we don't want to take half of an odd number and square it. I'm getting fractions, right? So really, the only times that you conveniently want to complete the square is if you've got x squared plus bx where b is even. And then I think it's pretty quick. Probably the easiest way if you can't factor, right? But otherwise, you would just default back to the quadratic formula. Well, let's take an example. I want to review with you guys, because I think sometimes factoring gets overlooked as a possibility if a is not equal to 1. You might have been told if a is not 1, just don't bother factoring, right? And that's okay. But sometimes it really is not that hard to do. Okay, let's take just a second and talk about that. Let me. Okay, let's try this one.
What? I remember that's not even big. That's what we did all the time.
And
Okay, so let's look at this guy. Let's look at this guy. So you guys probably learned bottoms up, right?
Yes.
Okay, well that's okay, although I really don't like bottoms up in an honors class because it's not algebraically, you'll see why. You'll see why. So if we're going to use bottoms up, kind of the new way I think they're teaching it now in Algebra 1, they call it slip and slide, but it's the same thing, right? Slip and slide. I kind of actually like the slip and slide better just because, I'll show you why. So what was bottoms up? What did we do with bottoms up?
C by A.
C by A. Okay, so if we use slip and slide,
And they must add up. Yeah. And then you divide.
here's slip and slide. So slip and slide, you're always going to take the leading coefficient, after you've tried to factor out a greatest common factor, of course, right?
Yes.
You take the leading coefficient and you're going to slip it to the back and multiply by c, right? So that's, and this looks familiar, right? Then you get x squared minus 16x minus 80, correct? Okay? And then we're gonna do step 2, which is what? Factor. Okay, good. So we're going to factor this simple quadratic, that's x squared, so I know those are both x's. What magic numbers multiply to negative 80 and add to negative 16? Negative 20 and positive 4. And then step 3, we're always going to divide whatever the factors of negative 80 that we chose were. Call them the magic numbers. We divide the magic numbers by the number that we slipped.
Exactly what we did.
So I know, same thing, same thing. Just different language, but you're used to doing this. And then you'll reduce those fractions, right? Okay, so we reduce the fractions and we get x minus 5/4 times x plus 1/4. And then if after reducing the fractions, you still get fractions, right? They're not integers, then you slide the denominators up in front of the x and you get 4x minus 5 times 4x plus 1. That's what you learned, right?
That's more complicated than what we did.
I don't remember ever putting anything.
No, that's the same thing you did, for sure.
Well, we just left the 16, instead of dividing it, we just left it in front of the x.
Yeah.
So it'd be like 16x minus 20, and then you just.
Yeah, and then you just factor whatever. Yeah.
So we'd stop at 3.
We just ball out.
Well,
Oh, so you guys, I see, so you guys would put the 16 there.
Yeah,
and
and
then
then
you
get rid
just
of like.
factor out the 4.
Okay,
Yeah.
well, I mean, that's the same thing.
Yeah.
Yeah.
We just step 3 though, so we get rid of this slide.
Yeah.
Well, but then instead of step 3, you've got to factor out a common factor,
Yeah.
right?
Yeah.
Okay.
But
But here's why I really don't like either one of those methods. Because they're not algebraically true. They're not the same thing. Like when you, it's a trick that works, but I'm gonna show you a better way of, for you guys, this is a much better way of doing it. Much better way of doing it. This is the method I teach to my regular Algebra 2 class, but I do not teach it to my Honors Algebra 2 class. I prefer for them to do something that's algebraically rigorous. The thinking is the same, but here's my point. When you're trying to do algebra, think how you do algebra vertically on a page, right? You're going to have the next line is equal but transformed, algebraically transformed. You just execute algebra steps and you slowly transform what you start with to what you want to get, right?
Yeah.
Okay? Well, this is not equal to that, right? You get my point? They are not the same thing. X squared minus 16x minus 80. If I wanted to make that a valid algebra step, I would have to multiply this whole thing by like 1/16 or something. And then it starts to get more difficult. And why would you do it, right? See my point?
Yeah.
So what you'd have to do here, and this is what I teach my Algebra 2 guys, is you'd have to do this like in a separate box because it's a process that's not algebraically consistent with this. And then the last step becomes your next step, right? And that's okay to do, I guess. But I still don't like it. It seems really cheesy to me. So here's a different way to do it. So if we're going to factor, what was it, 16x squared minus 16x? So if we're going to factor that, right? Here's what we could do. Now, we're going to do the same thinking that we did before. We're going to find magic numbers that multiply to AC. Well, what's AC?
80.
Negative 80, right?
Oh.
Yeah.
And add to B, which is negative 16. Well, we did that. That's the very same thing we did right here. We found the numbers to be negative 20 and positive 4. So you have to do that thinking anyway, right? Okay, so we're going to find the magic numbers. What were they again? Negative 20 and positive 4, right? But here's the difference. Now we're going to do this rigorously, and we're just going to factor this by grouping. Okay? So what we do is we're going to split the B term into a sum of two terms with these coefficients. right? So negative 16x, and it does not matter the order in which you do this. It makes no difference. We could either put the negative 20 first and the 4 second, or vice versa. If it works, it's gonna work either way. And you might be thinking as I go through this, well, how do you know it's gonna work? It's guaranteed to work if you find magic numbers, right? Because you can't do, would you agree that the process we just did, it wouldn't work if you couldn't do step 2,
Yeah.
right? So you have to be able to find magic numbers anyway, to be able to use bottoms up or slip and slide. So nothing is different. We found the two numbers, and they're negative 20x and positive 4x, and once again, the order makes no difference. The algebra is going to look slightly different, but you end up with the same result, minus 5. Now you remember factoring by grouping, you need an even number of terms to factor by grouping, which we now have. And so if we split this into two separate groups, well, we're going to factor by grouping, and I want to rehearse the steps to that, because once again, I think there's a way of looking at this that's, as you get to calculus and you're more evolved mathematically, you might look at this a little differently than you did previously, right? So when we're factoring by grouping, what do?
Well, you take out the common first.
Well, okay, we work in group 1 and we take out the greatest common factor, right?
Yeah.
So what is the greatest common factor? 4x. So we factor out a 4x, which leaves us behind with what?
4x.
Okay, good. So now the two groups were linked by this plus sign, right?
Yeah.
And even if it was minus, I'm going to put a plus in the middle to add the two groups. But I factored the first group into a product of a greatest common factor and a leftover, right? Okay, now working down the template here, what I'm going to want to be able to do in my next step, you got to kind of look ahead a little bit. I want to have a common factor in group 1 and group 2, and the common factor is going to be my leftover factor. Okay, right? You remember doing this?
Yeah.
So then that tells you right away that whatever you got there has to be the leftover factor that you get in group 2 as well. They automatically have to be the same thing or this process won't work. So without even thinking, you can just write down a 4x minus 5 and then just answer the question, what do I have to factor out to make that happen? In this case, I just factor out a 1, right? Okay? And so then if I factor out my greatest common factor from each group, look what I get. 4x minus 5 times
4x plus 1.
4x
I like this.
plus 1, and we got it, right? But we got it in a way that's actually legitimate math. I mean, those are algebra steps that all make sense. Each step is equal to the step preceding before it, right?
Yes.
Okay?
You do get the same value.
You do get the same value. You're right. To me, this way is a lot easier, though. I mean, you don't have to do some side math. I hate doing side math. You don't have to go do some side math and then get an answer and plug it in. It's just one continuous process. Okay? Anyway, a little review. Okay, so let's continue on with this then. So we know here that our discriminant was a positive number that's not a perfect square.
Yep.
So that means we're gonna use quadratic formula. Okay? You guys remember the quadratic formula? Sorry?
Yeah.
I think we need to listen to
Minus square root b squared minus 4ac all over.
No, divided.
Yeah.
Oh my goodness.
Okay. I think we need to listen to it tomorrow.
Yeah. Okay, so what do we get for our answers then? If we plug those in, we're gonna get positive 2, right?
Yeah.
Positive 2 plus or minus the square root of 76. So that's got to have 4 goes into that. So that's going to be 2 times the square root of 19, right?
Yeah.
No, yeah, 19, there we go.
Sure.
All over 6. So we're going to get the solutions then. We're getting 1/3 plus or minus square root of 19 over 3.
Yeah.
So let's just turn these into decimals. Somebody on your calculator, what do we get then? If I take the plus sign, what does that work out to be roughly as a decimal? Just out to like one place is fine. getting 1/3 plus,
Oh.
it's like 4.5-ish.
Yeah.
What is it? Somebody do it.
Yeah, just square root of 19 over 3.
Plus 1/3.
It's 1.8.
What?
Yeah, that's what my calculator
Yeah,
said.
that's why I got 32.
And then the other answer.
Oh, yeah, you never mind. That's right. Yeah, about 1.8. Okay. And then what's the other one gonna be?
Negative 1.1.
Okay. So we get our two, those are our approximate values. I want the decimals though so I can put them in my table at the right places.
Yeah, yeah.
So then we end up getting answers. I'm just gonna put in the decimals, okay, but we know what those really are, right?
Yeah.
So we get something like 1.8 and negative 1.1. And so let's know what's going on. Let's use our table and try to figure out what's happening there. So those, what else can I fill in on my table? Okay, yeah, what is f prime at those places?
0.
0. Okay, that's good. If it's 0, then that's telling me I've got horizontal tangents.
Correct.
And now I'd have to pick some test points.
Yeah.
What could I pick for test points?
0.
0. 0 is an easy one to evaluate my derivative at, isn't it? If I plug 0 in, I just get negative 6.
Yep.
Okay? So that's negative. Negative, okay, and then what if I pick like negative 10?
Oh. That too.
If I take negative 10, I like to take extreme ones so it's easy to see. So if I take negative 10, I'm going to get a positive answer, aren't I?
Yeah.
Okay, everybody see that for my derivative? So that's positive. And then if I take like positive 10, I'm obviously getting a positive one, right?
Yeah.
Okay? And so we know then that what's the nature of this guy? We're going increasing to decreasing. So maximum, decreasing to increasing, so minimum. Okay? So here's my goal then. I want to see if we can, let's find out what the second derivative is, and I want to see if you guys can tell me what that meaning of the second derivative is based on what we find. Okay? So if we differentiate this again, now the good news is, when we differentiate a polynomial successively, it just always gets easier, right?
Yeah.
So what is the second derivative?
6x minus 2.
6x minus 2, okay. Just for kicks here, let's figure out where is the second derivative equal to 0? 1/3, okay? And it's nowhere undefined. I'm going to put that in on the table. So 1/3 is going to fall like in between here somewhere, right? And in fact, I'm going to go ahead and just erase all these test points even. Well, I don't have to do that. I'm not going to get crazy. We'll go 1/3, which is right, oops. We'll go 1/3, which is right here. And that's a 0 of my second derivative. Is that going to slide too much stuff? Yeah, it does. All right. All right, I got you. I'm going to add another row. So 1/3 was the 0 of my second derivative, and if I wanted to find the intervals where it's positive and negative, where's it going to be positive? To the right of 1/3, bigger than 1/3 or less than 1/3?
Big.
Bigger. Everybody agree?
Yeah.
So values like 10 would give me a positive second derivative, and values like negative 10 would give me a negative second derivative. Okay? Let's just look at this function on a graph here for a second and see if we can make sense of what we already know. So if I just look at so there's the function, right?
Yeah.
Okay, do do the values, what do I have labeled here? I want to get rid of that. Okay. So the values that we had were like 1.8 is right here. Like if I want to look at the minimum and the maximum, if I click on this thing, there's my 1.8 and there's my negative 1.1.
Yep.
Right? And like we said, maximum and a minimum. Okay? But what is happening at the point when x is 0? Right? So if I pick a equals 0, or actually 1/3, right?
Yeah.
1/3 is where the second derivative was equal to 0. We said that everything to the left of 0, the second derivative was negative, and everything to the left of 1/3, the second derivative was negative, and to the right of 1/3, it was positive, correct? Okay, yeah, we got it. This is what we want. If we can get this today, we're in great shape. This is what we're trying to figure out. What is the meaning of that, right? To the left of 1/3, second derivative was negative. To the right, it was positive. And this is the result we see on the graph. Okay, what's going on there? I'm going to stretch this out so we can see this just a little bit better. Yeah, something in it. Yeah, we got to make sense of that. What's going on there? And to make things maybe just a little bit easier to see, I'm going to go ahead and put a vertical line in so we can kind of divide things up. So think what you got an idea? What do you mean by that?
It's the middle.
Okay. Yeah.
Is that where the slope is the steepest?
I mean, we're getting kind of to the point. Now let's back up a little bit. Here's always a good way to think about when we're thinking about derivatives. There's a relationship. First of all, let's think about something we know well. We know what the first derivative means relative to the function.
Yeah.
What's the meaning of the first derivative?
It is the slope.
It's the slope, right? So it's the rate of change of the function, or rate of change of y with respect to x, right? So if that's positive, that means that an ant walking from left to right should expect that his y value is going to be increasing as he moves to the left, right? We get that.
Mm-hmm.
Positive slope, negative slope. Okay, that's all the derivative is a rate of change. Now the second derivative is complicated to think about the second derivative, the relationship maybe to the original function. We'll get there. But let's consider the relationship of the second derivative to the first derivative, right? Okay, yeah, so the second derivative is the rate of change of the first derivative with respect to x. Right? So where the second derivative is positive, we should expect the first derivative to have a positive rate of change. Now don't confuse that with slope though, right? We're talking about the change of the slope, the rate of change of the slope with respect to x. So think what that would look like. If the slope is changing in a positive way, what's it doing? So if it was here and I move to the right and it's changing in a positive way, what should happen to the value of the slope? Should increase, right? Doesn't that mean that the slope is increasing if the second derivative is positive? If the second derivative is negative, the slope is decreasing as I move to the left, right? Okay, what does that mean about the topology then? If the slope is increasing and I'm moving to the left, what's the ant going to see ahead of it?
Hill.
The hill's going to be getting steeper, isn't it? Right? You see what I'm getting at? If the slope is decreasing, he's going to see the hill getting less steep.
Yeah.
So we call that concavity in math. Right? The concavity tells us what's the sort of like the curvature, what's the bend of the function. Is it bending in an increasing way or in a decreasing way? We can think of it in terms of a tangent line. If there's a place where the slope is decreasing, where is the curve going to sit relative to the tangent line? Is it going to bend up above the tangent line or below the tangent line? If the rate of change of the slope is positive, it's going to be bending above, isn't it? Right? Because the tangent line, the steepness of the tangent line should be increasing as I move to the right. Okay? So I think I've got this thing hooked up. So this will work. Let me get my tangent line here. Yes, there's my tangent line, right? So if I drag x back to a place where we know that the function has a negative concavity, look what we see. The curve sits below the tangent line. Okay, that's a negative concavity or a downward concavity. If I drag it up to a place above 1/3, and once again, right out 1/3, notice that we're in a point of transition, aren't we? To the left over here, in the region where the second derivative is negative, the curve sits below the function. To the right, though, where the concavity is positive, the second derivative is positive, the function sits on top of the tangent line. If I go over to this part, don't we see that? That the function always sits above the tangent line? So then that 1/3 is a point of transition, right? That's a point of transition of the concavity. We're going from a concave down region to a concave up region. A way to visually think about that, I think the tangent line test is the best way to test the concavity. But there's a visual implication too. What does it mean to be concave? It's like cupped, right?
Yeah.
So a region where the concavity is negative or concave down, the function is going to be bowl-shaped downward. So if there were a two-dimensional rainstorm here, a place with a negative concavity would shed the water, right? Whereas a place with a positive concavity would tend to catch the water because it's bowl-shaped up. You get the idea?
Yeah.
And so the place in the middle then, the transition, is what we call an inflection point. That's the meaning of inflection point in calculus. It's going to be a point of transition from positive or from negative to positive or vice versa of the concavity. Inflection points are important places, but that's how we recognize what they are. Okay? So then, a good definition of an inflection point is a point where the graph of a function has a tangent line and where the concavity changes. So it has to be a place where the tangent line exists. I'll give you an example of why that's important. Maybe you can tell me. And that's a mistake. Well, I won't say mistake. That sounds bad, but that's something that I don't think is always, well, I'll give you an example of where you can fall into a trap with this. And I've even seen this like in textbooks. But this is definitely true. So what if we have a place right here? Can you think of a place that might seem like it should be a concavity? What am I going to draw here? It might seem like it should be a concavity because we're changing, or an inflection point, sorry, because we're changing concavities, but in fact really shouldn't qualify.
Is it a sharp?
Yeah, what if we did something like this? What if we had a curve that went like that and then went like that? That's not an inflection point, right? It's not an inflection point because it's not a place where the derivative even exists. And in order for us to calculate a second derivative, don't we need a place where the derivative exists? Think back to the relationship between a first derivative and a function. What's the first thing we did? We found the domains. We could even just find the places where critical numbers make sense, right? The derivative doesn't exist where the function doesn't exist, and so a critical point couldn't exist there. Same thing is true for the second derivative, right? We only really want to look for inflection points where the first derivative exists, right?
Josiah Badola, Christopher Charpentier, and Jasmine Arizaga to the attendance office, please.